Hello everyone, my name is Tefik. Today I'm going to present the part number 4 of our video series, which is transformation of von Mises yield criterion into an ellipse and circle so that we could use it in the design limit equation. So before we get into the derivations, let's review what we have covered in the part 1 to 3. So in the part number 1 we covered the uniaxial burst rating, which had a delta P of positive, so internal minus the external pressure, so it lays in the upper part of the design limit plot. In the part number 2 we covered the collapse rating or collapse regimes of API. You remember there were 4 different collapse regimes, and we had this special area where where we had the positive tension. Therefore, it was the rating, the collapse rating. On the part number 3, what we have covered is the compression and the tension limit of the pipe, and also we have mentioned that some of the special pipe might have some lower performance ratings on the connection compared to the body, like the special clearance casing, like 1178 or 978. So today's topic, as we mentioned, is to draw an ellipse. How we gonna draw an ellipse for a known for a special for a known yield strength pipe, for example a 80 pipe or a 958 casing, for example. How we gonna plot it? So let's move into the left hand part. So we pull this equation here with the 3 principal stresses. If you remember, on the left hand side we had the yield strength, and then on the right hand side we have the tangential, radial and axial stress, and the torsion being 0 because we are not rotating the casing. So when we move here and then we expand the brackets with basically they will become like a tangential square plus radial square minus the 2 times radial times tangential. So we apply that to each of the brackets, and then we end up with an equation whereby we are cancelling the 2's on both sides. So we will end up with yield strength square will be equal to tangential stress square plus radial stress square plus the axial stress square minus the multiplication of the tangential and the radial and the axial and the tangential stresses. So here let's pause for a moment. So in an ellipse, if you want to represent as a mathematical formula, it will be some kind of a x square plus y square minus x times y. And then in this context of the von Mises, or in this context of the yield criterion, we will make it equal to yield strength square. So that's the point where it is equal to the yield strength of the pipe, or greater than the pipe where it starts yielding. So as you can see, I marked each term with 1, 2, 3, and 4, 5, and 6. All right, with green. And as you can see, our purpose is to come up with something like squares and a same and the multiplication of these, the root of x square and y square, so x and y. Here what we can say is we could find this, or we could spot these 3 terms, and then immediately we could think of, can we write this in a format of tangential minus the radial stress square and related in some kind of a conversion. So when we look at it, yes, we could write it. How we can write it? So it will be tangential square minus radial square. So what this gives us, it's gonna give us tangential square plus radial square minus 2 times tangential and the radial stress. So in order to obtain 1 plus 2 plus 3, we need to add a term called tangential stress times the radial stress. So that's gonna give me 1 plus 2 plus 3. And then let's look at the components 4 and 5 here. What we can say is it looks like I can write this into kind of a axial stress minus radial stress to the square. But if I expand that one, 4 plus 5, it will take the form of the axial stress minus radial stress square plus the multiplication of the axial stress times the radial stress minus the radial stress square. Why? Because if I take the square of 1 and then if I add these two, I will obtain the total of 4 and 5. All right. So if I combine everything, basically 1 plus 2 plus 3 plus 4 and 5, which is basically this equation, and number 6 that I haven't used in any of the conversions, then it will become like a tangential minus radial square, okay, and then axial minus radial square. So let's put this in one term because they are all square. So it starts to look like this equation, as you can imagine. So I have the x as being tangential minus radial, and then y being axial minus radial, okay, and then but I need this x minus x times y term as well. So can I have that one? So let's look at the remaining terms. So I also renamed these terms as a, b, c, d, and then if you sum this up, so that's tangential multiplication of tangential times radial, and then the axial times the radial, and then you have a minus radial square as well, and then you have a axial stress times the tangential stress. So if you put this here, immediately I can notice that I can basically pull radial stress into a bracket, okay, as a common term, and also I can put axial stress as a common term. And what I'm going to end up is basically is minus axial stress minus radial stress, and multiplied by the tangential stress minus radial stress. So as you can see, this one now looks familiar to xy, where I could say that x is tangential minus radial, and then y is axial minus radial stresses. So here we come back again. So I put an arrow here. So that was our initial aim in building a triaxial ellipse format for our design limit plot. So now I know that my x become I found out that it is tangential minus radial stress to the square, and then y is axial stress to the axial stress minus radial stress to the square. So that will be the y square, and then that will be the x square, and then you have the multiplication of the x times y, which are basically tangential minus radial stress to the for the x, and then for the y you have the axial stress to the radial stress. Writing in this form will give us some benefits, which I'm going to show on the second page. So until now I didn't plug in any of the principal stress formulas with, if you remember, with internal and external pressures, internal and external areas, because this way it simplifies it. So what we have done basically is we take this von Mises-Yield criterion and then we put it in a kind of a math formula, so that we could easily pull the x and y with some simple term, the difference of the tangential and the radial stress, and the axial and the radial stress, and then x and y is here. So the next step, what we are gonna do is we are gonna use each formula for the principal stresses, and then we will replace them with their internal and external pressures, areas, and then try to come up with a formula so that we can pull the delta P here, delta P versus something, and then that will be axial tension or compression plus a backup pressure. It will be an internal or an external pressure, but the aim is to find delta P, and then derive the delta p, and then we will be able to draw an ellipse for each of the different casing grades or the ID and OD combinations. Okay, so this equation, you remember, it was from the previous page. So that was the x, that was the y, and then that was the x and y. So this was kind of an ellipse equation, right? So if we look at the principal stresses here, what we could see is basically you know, the internal area, internal pressure, into outer area, external pressure. And as you can see in the tangential and radial, you have one of them is plus, one of them is minus, right? So this was the general equation. And then to simplify this a bit further, what I have done here is, you remember the our internal radius square and the outer radius square and the outer radius square minus the inner radius square. So what I have done is, instead of inner radius square, I just simply called it inner area, and then this one I simply called it as outer area, and then the difference in the pressures, I simply call this as delta p. So why I mean, simply inner area is basically pi times inner radius square to the 4, but pi over 4s on both sides, they will cancel. So this way of writing makes it much simpler. So when I look at the difference between tangential and radial, I could immediately see that when I take the difference, this will cancel out, and then if I evaluate the principal stresses in the inner wall, meaning that because it's the yield first start from the inner wall, then I could see that I'm getting a difference of 2 times delta p, which is the internal minus the external pressure times the outer area divided by the cross-sectional area, which is outer area minus the inner area. So this delta p is basically regardless of regardless of my internal, external pressure area, inner area, outer area, or the cross-sectional area. It's independent of it. So you take the difference, and then that you will end up with this one. And then let's look at the axial stress plus the minus the radial stress difference. So radial stress being the smallest, you know, most of the time, in the absence of any bending, is basically can be evaluated at the inner wall as minus internal pressure. Why? So you look at this equation. So in the if I take this one delta p, if I expand it as internal minus the external pressure, and then if I write the cross-sectional area as outer area minus the inner area, you can do yourself. It will come at minus internal pressure. Again, this is regardless of the outer pressure. This is regardless of outer pressure, outer area, or the inner area. So we are coming to a simple solution here. So we have the radial stress, and then we have the difference between the tangential and radial stress. So I will plug these figures into our main equation, which was, you know, you remember the difference between tangential minus radial stress square plus the axial minus the radial stress square minus the multiplication of the product of the tangential minus the radial and the axial minus the radial stress. So I pulled that equation over here, okay, and then I replaced each term, the differences, with their terms, okay, and then I end up with this equation for the yield strength, okay. So, and what I'm gonna do is I'm gonna pull this yield strength to the right hand side. So it will be minus yield strength square is equal to 0. Why I did that? Because if you remember from the earlier math or calculus lessons, for quadratic equation, which is ax squared plus the bx plus the c is equal to 0, you can find the root for x, and then that will be minus b plus minus the root square of b squared minus 4ac divided by 2a. So that is the kind of the root square for x if you want to full the x. So why we want to find the x? Because here for x for us is the delta p over here. I mean, like, why we want to find a delta p? Because we want to plot the corresponding value of delta p. I'm saying delta p is x here, but actually in our design limit plot, delta p is presented on the y-axis, on the ordinate. But just to have some similarity with this quadratic equation, I'm calling x as delta p because we need to find the root of it, root of the x. So in this format, x is delta p in this format. So it will be kind of, if you put this into kind of ax squared plus bx plus c equation, delta p, we will find it as the root is equal to, delta p is equal to minus b plus minus the square root of b squared minus 4ac divided 2a. So let's expand the formula a bit more here. So what I need to do is, I have some common terms here. Okay, I will rename them so that I can make them easier to work out later on, because then I will be able to pick what they stand for in the longest formula, rather than carrying those big long ratios, area ratios or whatever in to the final formula. So I have here 2 times outer area divided by the cross sectional area, and here as well. So I will mention it, I will rename this as AR to the subscript I, R, which will be named as area ratio, or which will be referring to area ratio. And then also I will write axial stress plus the internal pressure as AX, as the axial, all right? That will be your x-axis over here. And then why I need that? Because you will see later on that when we plot it, it will be plotted on the lower side of the design limit. So the backup pressure, when we talk initially, that PI will be a backup pressure for a collapse case, because collapse case is the pressure resisting to collapse is the backup pressure, is the internal pressure in that case. So when I put this into the simplified terms, it will be AR squared times the delta P squared minus delta P times AR times AX. Those were being, you remember, 2 times the outer area divided cross sectional area times the axial stress plus the backup pressure, which is the internal. So that will be drawn on the bottom side. So it will be some kind of a, it will be drawn like this on the so this will be let's say this solution. Okay, so delta P, this solution. All right. So then I have the perfect quadratic equation here. So ax squared plus bx plus c is equal to 0. So that's the exact equation here. So here we can pull the a, b, and c for our quadratic equation. A would be AR squared, all right, and then B would be AR times AX, and then C would be AX squared minus the yield strength squared. So when I pull the delta P over here from this formula, so I will pull for the X, which is I will pull for the delta P. Delta P would be minus B, okay, which was the AR times AX, that's here, okay, and then plus the B square, so that was the B, so I take the square, and then minus, I take the 4, and then I take the A times C, AX square minus yield strength square, divided by 2A. 2A, what was the A? AR square, which was the AR ratio, which was the simplified form of 2 times the outer area divided the cross-sectional area. So I will put that in the denominator, and then I will find the delta P as minus ax divided by 2ar plus minus the one of the root, and then into the square root of ax square times ar square. So I have this ar square, okay? So I basically separated this equation into two. So this part divided 2ar square, and then plus the square root term divided by the 2ar square. So this 2ar square I will pull into the square root as 1 over 4 times ar to the 4, alright, into the square root. And then when I simplify the terms, it will be an equivalent, that root square, it will be an equivalent to ax square plus 4ar square minus 1 over ar square times ax square minus the sy square. So you could see that if I basically put 4 to make the denominator same, and then I pull this into the same line, I could see that this square root is simply 1 over ar, which is the 2 times outer area divided by the cross section. It will be simply 1 over ar, and then into the square root is minus 3 over 4 ax square, which is this stress plus the backup pressure for internal, and then plus the yield strength square to the square root. So then what is gonna happen is, so I have the square root here, and then I have this term over here, if you remember. So I will pull both of them here, and then what I need to do now is I will write ax and then ar, and then replace them. So ax, what was it? Axial stress plus the backup pressure for the collapse, which was the internal pressure, and then I will pull the ar, which is the 2 times the outer area divided by the cross section area. So I will pull these and then replace the ar and ax, and then what I need to do here is there's a yield strength square here. So because I have that one, what I need to do is I will multiply this full formula by S yield strength and then divide by yield strength. So it's effectively, I'm just multiplying the equation with 1, which is effectively this, it will be same equation, but I want to kind of come up with a workable or with a workable formula where I will compare the axial stress plus the backup pressure to the yield strength. Okay, so that's why I will want to make this term as a ratio to the yield strength, which I'm gonna I will tell in a second why it's important. So when I have that when I do that, I will pull the sy into the 1 over sy as a 1 over sy square into the root. Okay, because 1 over sy was outside, I will put into the root, square root as 1 over sy square, and then what's going to happen is the equation will look like stress plus the internal pressure backup divided to the sy square, 3 over 4 over here, 1. These are very familiar terms for you, and then here also the ratio of the stress plus the backup pressure for collapse divided by the yield strength. Because why I say this equation, if you remember, this was the duration for collapse when we covered the collapse in the part number 2. So it wasn't derating the yield strength, but it's gonna come. It was giving kind of an equivalent yield strength, so that you will put the equation back into the collapse regime. So what happens is I have a kind of a tension or a compression and a backup pressure, and then I will take into the yield strength. I will take the ratio. If it's a tension, then my collapse rating will be derated, and then I will come up with a delta P versus something, which means dear petrol engineering students and the drilling engineers, which means for any delta P over here. For any delta P over here, I will basically find an x. So this is, let's say for example, that's x plus y coordinate for this point. So if I put my delta P, all right, if I put my delta P, I will be able to find the x, which will be the stress plus backup, or in a more simplified term, you could basically make any Excel table with some pre-filled tension values from 0 to, I don't know, whatever the yield strength and the cross section of the pipe, but 0 to maybe 1.5 million pounds to minus 1.5 million pounds. So it covers a range from tension to compression, and then you will be able to find the corresponding number for the delta P. So what's gonna give you is it will give you a point as a load case, let's say. But to draw the ellipse for a given tensile strength of the pipe, you can give a range of tension to compression. You know the pipe properties, you know the yield strength, you know the outer area, you know the inner area. You will be able to easily for the delta P. So you will have all these lines, all right, to make the ellipse, which is the lower part of the ellipse. But for the load cases, you will be able to still work out where the load cases are laying compared to the ellipse. So in this page, we basically worked out a solution to find the corresponding delta P to a known tension. So this formula is the triaxial formula, which means we are accounting for the tangential stress, we are accounting for the radial stress, and we are accounting for the axial stress. So we are not doing any biaxial where we are ignoring a radial stress. No, all three stresses are accounted, because it's maybe none of the time where each one stress is acting. Most of the time or all the time, three axes are basically acting on the pipe: radial, axial, and the tangential. So all of them are included here. So delta P, you will find the stress corresponding to your delta P, and then that will let you to draw the bottom part of it. So please take a note of this equation, because I'm gonna use the same equation to find the delta P with a backup of external pressure, and then that will be the backup for the burst load cases, which will be drawn on the top of the design limit. Okay, thank you. Okay, so we have just derived basically the bottom part of the design limit in the triaxial state, where we basically found the delta P with the axial stress plus the internal pressure as backup, which are the apply for the collapse load cases. So the internal pressure tends to resist the collapse. So that's why we have done the bottom part of the triaxial state. So now I'm gonna derive the equation for the upper part, which means for the burst load cases, the external pressure or the outer pressure applies as a backup against burst. So what I'm gonna write is internal pressure. I'm gonna write this as basically outside pressure plus the delta P. Why? Because if you remember delta P was simply P internal minus the P external, and then I know that I have derived this general formula from principal stresses with the internal pressure. So I will replace the internal pressure with basically internal pressure is equal to delta P plus PO. So I'm gonna replace delta P here and delta P, I'm going to replace the internal pressure and internal pressure here with simply delta P plus the external pressure or outer pressure. So if I take the simple items from the squares, this will be, as you know, is 4 times delta P square times outer area square divided by cross section square. And here, when I replace my internal pressure with external pressure plus the delta P, I will simply write as 2 components. So stress plus the external pressure as backup, and then plus the delta P as a separate item, so that I could basically take the squares easily. And then here I replaced also my internal pressure with the external pressure plus delta P as a confirmation, so as a transformation. So I did the transformation over there from internal pressure to outer pressure plus the delta P. So continuing our derivation, taking the square. So I take the square of this one. So as you can see, stress plus the outer pressure as backup, square plus the delta P square plus you have the product of two items plus 2 and minus I also did the same thing here. I separated the stress plus the external pressure as backup plus the delta P. I separated these two items so that I could easily multiply this one first and then multiply this one and then basically expand the formula so that it's easier for us. Like in the previous one, I renamed the formula with some letters. So each component. So I call this as A. That's the square of this item. Okay, and then I renamed the delta P square as B. And then I put stress plus the backup square to the square as D, and then this one stress plus the backup pressure times delta P minus this term, and then this term as E, F, and C. So why I have done that one? Because as you see, you have delta P square on A, B, and C over here. So I can group it easily in the bracket. And then here you could see that in D, E, and F you have the axial stress plus the backup pressure for the burst, which is the external pressure. So when I did grouping, so grouping by delta P square over here, and then grouping by the stress plus the external pressure, I could see that the yield strength square, it will be equal to, so delta P square grouped into 4A outer area square to the cross sectional area square plus 1. Okay, this 1 is coming from this delta P square. Okay, and then minus 2A outer area divided by the cross sectional area, and then that's coming from the item C. All right, and then you have the D over here, and then you have the E and F here, and then for E and F, as we mentioned, we will group into this 2 times the axial stress plus the outer pressure as backup times delta P into here. Okay, so if I expand all these areas, so I need to make a couple of renaming or expansion over there. First of all, the cross-sectional area is, as you know, is outer area minus the inner area, and then cross-sectional area square will be AO minus AI to the square, which will mean outer area square plus the inner area square minus 2 times the inner and the outer area. So when I expand this one, and then all the denominators, I need to make it AS square so that I can group them in one line item over here. As you can see, there is 2 times inner area times the outer area, and then there's plus here, there's minus here, and then plus here, so they will cancel each other. So and then you have the 4 times outer area square, 1 times outer area square minus 2 times outer area square, so that remains as 3 outer area square, and plus you have 1 AI square over here, and on the denominator you have the AS square, cross-sectional area square. So that's the A plus B plus C, so that's this term. And then once we group let's look at D first. D will remain as it is. However, because this quadratic equation, the solution is ax squared plus bx plus c is equal to 0, we will pull the yield strength square to this side. So that's why this d and sy square will remain over here. That will be a new c over here. And then for the en plus f, it will be kind of a 2 axial stress axial stress plus the outside pressure as backup, delta P, and then 1 minus 2 times outer area divided by cross section. So this equation, as you remember, is similar to this one. Ax squared plus bx plus c is equal to 0. So it's a quadratic equation. And then we will again solve for delta P, for the root of the equation in terms of delta P. So we could correlate delta P to some kind of an axial stress and the backup for the burst section. So we could easily see that here my x is delta P. All right, my x is delta P because I'm referring to the quadratic equation. In our design limit, our delta P is on the y-axis. So don't confuse that one. So here I have the x squared as equal to delta P squared. So x is basically delta P in our case. A is this term over here. So 3 times outer area squared plus inner area squared to the cross-sectional area squared. All right, and then our new B to correlate with our quadratic equation will be 2 times stress plus the outer pressure as backup times the 1 minus outer area divided by cross section as new B. And then our C, it will be, because it will be equal to 0, we put the yield strength to the right hand side. It will be kind of a stress plus outer area square minus the yield strength square. If you remember, when we do this, when we find the initial solution for the internal pressure as backup, when we have done this one, as you remember, our C was stress plus the internal pressure minus the sy square. So this is also similar to that equation in terms of stress and the yield strength. So then coming on to this lower right hand corner, what happens is we basically pull this one as the root of for the delta P is minus B plus minus square root B squared minus 4AC divided by 2A. So we know our B, what was the B is this component, and then we know the A was this component, basically areas, some area ratio to the cross sectional area, yeah, and then we know the C was the basically stress plus the backup pressure to the square minus the yield strength square. So then if we just basically put in this format now, and then we will do the same thing as this equation. So we will divide it and divide and multiply at the same time by sy over sy. So it's basically 1, but it will show us a ratio of basically strength over the axial stress plus the backup for outer pressure for burst on the upper side to the yield strength. So why I'm saying this, because we know that for uniaxial burst limit that we have studied on the part number 1, we know that that's uniaxial, no axial stress is considered on that case, but we know that some tension is tends to have improvement on the burst rating. So that's why when we plot the axial limits, it will tend to some uniaxial API limits over here, uniaxial burst limits. You will see that this, especially this part of triaxial limit, will tend to exceed that uniaxial limit. So that's why we will need that ratio from stress plus the backup outer pressure to yield strength on everything. And then we basically, like this one, we have obtained a solution for our delta P to a corresponding stress and the backup pressure in a given for a given pipe. Sorry, for a given pipe with a let's say a specified yield strength, minimum specified yield strength. So let's say for a 958 L80 pipe, I know that from the nominal wall thickness, I know that the outer area, cross-sectional area, yield strength, okay, and then I can basically define a set of axial stress from a minus to a plus, so it's from a tension to a compression range, and then I will be able to find the associated delta P for the burst side. So I put it in green over here. So when we plotted this one, when we find corresponding delta P values to stress plus the outer pressure, it will be plotted on this side. So we have already done this one on the previous derivation, and then we have completed this part currently, so that once we combine everything, it should be one ellipse. And just to reiterate one thing here, at this moment here, your axial stress here, when your axial stress plus the internal or external pressure, it will be P is equal to P. So at this point, these two points on the upper side and the lower side, they should correspond. But sometimes there might be a kink, I think. Okay, so then we go to the second page. So now we have basically proven two things. Once we proven this side, and then we have proven this side for the triaxial limits. So we could basically say that there is two solutions how to build an ellipse in the Excel for our part number 5. So we know that we derived both equations, right? We derived both equations on the previous pages. So you could derive delta P for a set of stress and the backup pressures, including a specified part with the outer area, inner area, or some yield strength. The second solution that we are going to talk about is basically build an ellipse based on Dr. Steven Kuczynski's video. So when I was interested in building the triaxial ellipse, this was the first thing that I came across. He made a really good video. Basically, it's working on basically a transformation of an ellipse into an ellipse. Transformation of a circle, then into an ellipse by some radial transformation. So I will put the link at the bottom of the video so you can go through that. But I will simply call this method as semi-major or semi-minor method, because this is how we're gonna tackle this. So he basically what he has done is he drew an ellipse, and then he called the semi-major as A and then semi-minor as B. This is ellipse, if you remember, for example surveying, when you are drilling the well, for example in a ERD well, your errors that associated with your axial or axial errors or the imbalance in the drill string. As you know, the error is in a format of an ellipse, and then it has both a semi-major radius and a semi-minor radius, so that at the TD you have kind of an ellipse uncertainty where the well is located. So let's come back to our subject. So he called this as A, semi-major, and semi-minor as B, and then what he has done is basically at this point you have the stress 1 and stress 2, and they are equal. Over here, however, your stress 2 is equal to minus of the stress 1. And here, in a general formula, for example, is principal stress 1 square plus principal stress 2 square minus principal stress 1 and 2 is equal to some square. So in our context is the yield strength square, right? And then we know that the principal stress 1 is basically, we derived it, if you remember, that's tangential minus radial stress, and the principal stress number 2 is axial minus radial, or is axial plus pi, because we evaluated, you remember, at the inner wall. And here, regardless of the external pressure or internal pressure, it is equal to 2 times delta P times outer area divided by cross-sectional area. So that's our case. So don't forget it. We will apply this when we transform this into an Excel. So that again, this is the solution number 2 of drawing an ellipse. And then in the part number 5, you will see that solution 1 and solution 2, they give very similar ellipses. However, solution number 1, we know that we use the principal stresses, so it's an exact solution. All right. So in the semi-major, the basic trigonometry. So if it's 1 here, principal stress 1, what will be the A semi-major? It will be the principal stress number 1 times square root of 2. That's coming from sine 45 or cosine 45. It's same over here. And then we know that if you use the principal stress equation, A will be equal to yield strength times square root of 2. If we try to evaluate the semi-minor of B over here, so B has the same equation. It's a hypotenuse. So it's stress number 1 plus the stress number 1. So these are squared on to the square root. Okay. So the B will be equal to square root of 2 times the principal stress number 1. Why? Because on this side, principal stress number 1, if you multiply that with minus, you obtain the principal stress number 2. Not like on this side, where they are all equal when we were finding the semi-major. So then we pull this into this, our principal stress equation for yield strength, and then we will see that principal stress number 1 is equal to 1 over square root of 3 times yield strength. And if you move the yield principal stress number 1 into the equation or correlation with B, you will come to the solution of B is equal to square root of 2 divided by square root of 3 times yield strength. So after this one, now we have the A and B. For a yield strength value in Excel, for example, let's take a 80K pipe. Okay, so that's LAT or NAT pipe. Okay, we will have corresponding A and B. We will have corresponding semi-major and semi-minor. So what we are going through as taught by Dr. Steven is we will go through some transformation from 0 to 2 pi. All right, and then we will transform the x-axis and y-axis, and then we will continue to transform to make an ellipse. All right, and then on that ellipse, all these points, which are basically corresponding x and y, which I called it x, y, and then x superscript and then y superscript. It will be depending on our principal stresses that we have basically derived moments ago. So that will be axial stress plus the internal pressure. All right, and then we will have also 2 times the delta P times the outer area divided cross sectional area. What they are on what? They are on the terms of our principal stresses, which are axial stress minus the radial stress and the tangential stress minus the radial stress. So we will come up with a ellipse like this on the part number 5 using the solution 2 for the ellipse. Next, I'm gonna derive an equation for the effective tension. So where the difference is coming from, guys? So for the ellipse solution on the x-axis, I have always a kind of a backup. So I have always a backup. So in terms of internal pressure or external pressure. So depending on the load cases of internal pressure and external pressure, this will move, right? If I want to make a design limit plot, all right, without being affected of the pressure, let's call it without being affected, or excluding a pressure effect on the x-axis, what I could do is I will plot it in terms of effective tension. which we have spoken in the part number 3. So next I'm gonna derive the equation so that delta P, we can associate the delta P with the effective tension on the x-axis. Okay, we just have finished deriving the von Mises yield criterion into an ellipse, and then now this step we are gonna derive it or put it into a circle form. So in the circle form, it's kind of a yield strength on all axes, and then it has got a general circle the formula of x squared plus y squared is equal to the yield strength squared. So we will try to find out x and y, and then x in terms of so this will be in terms of effective tension, so it will not have any backup pressure in it, but it's an effective tension. On the first one, when we derived it, they were all true tension when we have done it into the ellipse form. So what I need to do here is I have my general yield strength into a von Mises yield criterion, and because these were driven by the principal stresses, as you remember, I will transform the axial stress, true axial stress into the effective stress, and by adding plus x, and then x will be the minus of the outside pressure times the outer area plus internal pressure times the inner area. So when I expand the term over here, I will keep the axis for now, and then also I will try to expand cross-sectional area by the difference of the outer area and the inner area. And here, as you can see, I need to multiply this with cross-sectional area square of cross-sectional area, so that I can have all the items in one line. So I think here I basically expanded the squares, and here also I basically expanded while using x, and then I replaced the cross-sectional area by the difference between the outer area and the inner area, and then x with our conversion from true tension to effective tension. So I think probably it will not be very practical to go over all these terms. So you just need to basically expand all these terms. Yeah, you take the square of the brackets, and then you replace x, and then you replace cross-sectional area, and then you will end up with this long and then the number of components having internal area, outer area, internal pressure and external pressure, and the effective tension. But don't be afraid, because don't get scared, because at the end of the day they will cancel out some of them. So here, for example, like for example, cross-sectional area I expanded, and then you expand x over there, and then you expand cross-sectional area, and then you multiply with pi, so it gives you kind of a many members with having lots of internal, external pressure, inner area and outer area. And as I said, don't get scared. It will many items they will cancel each other. So we will end up with this numerator and denominator. So on the denominator we have the cross-sectional area square, and on the numerator we will have the effective tension square plus the outer area square times the outer pressure, external pressure square, minus 2 times the effective tension times outer pressure or external pressure times the outer area, plus internal pressure to the square, and multiply by the outer area to the square, and plus you have the 2 times effective tension. These items they look similar, but in fact one of them is the outside pressure and one of them is the inside pressure, so internal pressure and external pressure, and then minus 2 times outer pressure, external pressure, outer area, and the times the inner inside or internal pressure. So we will expand it, as I mentioned, we will expand it one by one, because otherwise it's gonna get too messy. So that's number 1 over here. So we basically converted the true state into an effective state, and then we are gonna now look at the item number 2, which is this term over here. So on the number 2, what's gonna happen is I will basically follow the same procedure of basically converting the true state into the effective state by having this x, and then x being the minus PO times AO plus PI times the AI, and then when you also write the delta P as internal minus the external pressure, you will get all these terms. So I will expand it, and then I will expand it, and then as you see there's x here, so I will expand the x, and then you see you will start getting like the outer area squares, pressure squares, like in the first expansion or first term expansion. So then what I'm gonna do is from the first page, the number 1 item that we expanded and the number 2 item that we expanded, I sum everything together, and then what I end up is basically effective tension square plus the 2 times outside pressure, outer area square times the internal pressure minus outer pressure, external pressure square times the external outer area square minus the internal pressure square times the outer area square. So as you notice, there is here you could take the outer area squares as a common item. So what you need to do is you take this as outside the bracket, so you can group these items, and then as you notice, this will give kind of a delta P square. So why I say that? Because you take the AO square into the beginning, it will be kind of a PI square plus PO square minus 2 times PI PO, which is basically effectively delta P square. So I put the note here. So that's the conversion of that one. So here what we need to do is, because there's one denominator, so I will separate this into 2 terms here. The effective tension square divided by the cross-sectional area square, and then that will be minus delta P square outer area square to divide by the cross-sectional area square. So as you remember, on the number 3, I haven't basically touched this term. That's number 3. Okay, so we expanded number 1, number 2. So number 1 being here and number 2 on the other page. So now I will take the number 3. Okay, so that's easy to basically calculate as 2AP, 2 delta P AO, A outer area divided by cross-sectional area. So we take the square, so that's basically 4 delta P square times the external area square divided by cross-sectional area square. So we have the 1 minus here, as you notice, and then that will be equal to effective tension square divided by the cross-sectional area square. This is kind of an effectively, this is a PSI term over here, because effective tension is in pounds, and then you divide by the cross-sectional area, you will get a kind of a PSI, but that's to the square. Okay, so that's to the square it will be, and then you will have the term on the right hand side. That's basically 3 times delta P square times the outer area square divided by the cross-sectional area to the square. So again, this will be kind of a PSI to the square. So now we have combined number 1, 2, and 3 from our von Mises yield criterion, from the one that we derive with the principal stresses, expanding them. But really that solution wasn't depending on any internal external pressure, inner diameter or outer diameter. That was just the principal stresses. And then on the left hand side, what was it? Yield strength square. So our equation simply becomes yield strength square is equal to this term and plus this term. So we know that the circle solution is basically x square plus y square is equal to yield strength square. So you will basically obtain a circle with a radius of yield strength. All the radius are on yield strength. So what we can see is here, x-axis is effectively, the x value is effectively becoming effective tension over the cross-sectional area. This is pounds divided by inch square cross-sectional area, so that will be in psi. And then the y-axis is also, this is y square, as you know, from this side. So if you take the square root of this one, you will end up with a square root of 3 differential pressure outside area and the cross-sectional area. That's on the y-axis. So what we can see from this one is basically I don't have any backup pressure on the x-axis. So any load case will have a effective tension profile. So when we correct it back to effective tension, then it will not have any it will not require any adjustment for internal or external pressure like we have done on the ellipse format, where your backup pressure, internal or external. So internal pressure for the collapse, and then the external pressure for the burst. They will need pressure correction, because the x-axis, you remember, it was basically stress plus pi or stress plus P as the backup pressure. Thanks for watching, and then on the number 5, part number 5, which is the last series of our video, proof of concept stress-based casing design. I'm gonna put all these formulas into an Excel, and then first we will review with Dr. Stevens' method to draw an ellipse, and then also we will investigate basically calculating delta P with given tension for a range of pipe, for a range of yield strength pipe and OD and ID, and then we will compare that, and then we will draw, of course, the uniaxial limits based on the API collapse regimes, uniaxial burst, and the the tension and compression limit of the performance rating of the pipe, and then we will use some example load cases to test them, how they are looking into the comparing to the design limits. So thanks for watching.